Welcome everyone to another video for pre-calculus. In this video, we are going to discuss about complex zeros and the fundamental theorem of algebra. So the fundamental theorem of algebra states that every polynomial function of degree n with n greater than or equals to 1 has at least one zero in the system of complex numbers. So every polynomial will have at least one zero. That could be a complex zero or real zero. We know that real numbers are also considered as complex numbers. So within the complex number systems, we have at least one zero for a polynomial of degree n. One consequence or one result of the fundamental theorem of algebra is every polynomial function p of x of degree n with n greater than or equals to 1 can be factored into n linear factors, and that can be written as this. So that means if we know the zeros, then we can write the polynomial using this format. Okay. So this one says find all the zeros of f of x equals x cubed plus 2x squared plus x plus 2 and write f of x in complete factored form. So what we are going to do is, I think this is pretty simple in terms of factoring. So we are going to group this and then factor by grouping. And so we'll group these two together and then we'll group these two together. So this means we have f of x equals, so we can factor out x squared from the first two, so we have x plus 2, and then the only common factor here is just 1, so we have 1 times x plus 2. Now from these two terms, we have x plus 2 as the common factor, so we have f of x equals x plus 2 times x squared plus 1. Now, the second, so we have the first linear factor here. This is a quadratic factor. We cannot factor that easily. So what we are going to do is we are going to find the zeros first. So let's go ahead and find the zero and then we'll factor it. So from here, so the zeros are given by x plus 2 equals 0 or x squared plus 1 equals 0. So from here we get x equals negative 2. From here we get x squared equals negative 1, which means x equals positive or negative I. So that means our zeros are negative 2, negative I, and positive I. So that means we can write the factors of this polynomial as f of x equals, so if negative 2 is the 0, then the factor is x plus 2. And then if I is the 0, then the factor is x minus I. And if negative I is the 0, then the factor is x minus negative I, which means x plus I. So this polynomial is written in the factored form. So we have a degree 3 polynomial. So we got 3 linear factors, and then we can write the polynomial in the factored form. So this question is asking us to find a polynomial of degree 3 having zeros 1, 3i, and negative 3i, and a condition is given that p of 2 equals 26. So let's go ahead and write the polynomial as p of x equals, so using this result of the fundamental theorem of algebra, we are going to write that polynomial as p of x equals a times, so the first 0 is 1, so the factor is x minus 1, and the second 0 is 3i, so the factor is x minus 3i, and the third 0 is negative 3i, so that means the factor is x plus 3i. So let's write it this way. Now this gives us p of x equals a times x minus 1. Let's go ahead and multiply x minus 3 and x plus 3. So they are conjugate. So we know that a plus bi times a minus bi is just a squared plus b squared. So when we that's how we multiply the conjugate, complex conjugate. So same thing here, x minus 3i times x plus 3i is just x is squared plus 9. Now we can go ahead and multiply those two factors. That gives us a times, so x times x is squared is x cubed, then x times 9 is plus 9x minus x squared and minus 9. Now if we distribute that a, okay, so before we distribute a, what we can do is we can use this given condition to find the value of a. So let's just write this in order and then we'll do that. So a times x cubed minus x squared plus 9x minus 9. So this says that when x is 2, the value of the polynomial function is 26. So we can write this as 26 equals a times, so x is 2, so 2 cubed minus 2 squared plus 9 times 2 minus 9. And then if we simplify this, we get a times, so 8 minus 4 plus 18 minus 9, and then that gives us 13. So 26 equals, so this is 13, so we have a, so this is 13a, and then we get a equals 2. Now if a is 2, then our polynomial is p of x equals 2 times x cubed minus x squared plus 9x minus 9, or p of x equals 2x cubed minus 2x squared plus 18x minus 18. And that is the required polynomial. Now there's another question. So let's go ahead and find a polynomial of degree 4 with negative 1 as the zero of multiplicity 2, 4 as the zero of multiplicity 1, and 0 as the multiplicity 0 as a zero of multiplicity 1 with this given condition. So let's do the same thing. So we'll go ahead and write p of x equals a. Then we have a 0, negative 1, so the factor is x plus 1, and it has a multiplicity of 2, so that means we put a square here. Now the next 0 is 4, so we have x minus 4 as the factor. The multiplicity is 1, so it's just the power 1. So the next factor is, next 0 is just 0, so it's x minus 0, and the multiplicity is 1, so we really don't have to put that. Now this equals p of x equals a times. So let's write this as x minus 0 is just x, then x times x plus 1 is squared times x minus 4. We can just leave it here and then we'll find a. We really don't have to multiply. We can multiply, but it might look more messy. So we'll just leave it in the factored form. And then we'll use this one now. So this says when x is 1, the value of the polynomial function is 6. So we are going to use that. So p of x is 6 when x is 1. So a times, so x is 1 times 1 plus 1 squared times 1 minus 4. And then that gives us 6 equals a times, so this is 2 squared is 4 times negative 3 is negative 12. And then if we divide by negative 12, we get a equals negative 1/2. That means the polynomial p of x equals negative 1/2 x times x plus 1 squared times x minus 4. If we want, we can multiply this one and write in expanded form, but we can also just leave it here. So this is the degree 4 polynomial as requested by the question. Now we are going to look at one important fact here. This is if we have a non-real and irrational zeros, or if we have a imaginary zeros or complex zeros and then irrational zeros, then this fact is true. So if we have a complex zero as the zero of the polynomial, then its conjugate is also the complex zero. So if we have 2 plus 5i as one of the zero of the polynomial, then 2 minus 5i must be the zero of that polynomial. Okay, so similarly, this thing is true when we have a irrational zero. So for example, if we have negative 5 minus 3 square root of 2 as the zero of a polynomial, then we also have negative 5 plus 3 square root of 2, which is the conjugate of this one, as the zero of the polynomial. So always non-real and irrational zeros, they always appear or always occur in conjugate pairs. So if one of the conjugate pair is the zero, then other must be the zero of that polynomial. Okay. So now here we are asked to find a polynomial of degree 3 that has an integer coefficient and then zeros, 1/3 and 2 minus I. So one thing, 1/3 is a real number, so we don't have the conjugate for that, but we have 2 minus I. That means if this is the zero of the given polynomial, then 2 plus I is also the zero of the given polynomial, because that is the conjugate. Okay, so now we are going to do the exact thing that we did for the previous example. So we are going to write the polynomial as p of x. So just give me a minute. So p of x equals a times, so the first factor is 1/3, so it's x minus 1/3 times x minus 2i is the 0, so 2 minus I is the 0, so 2 minus I times x minus, so 2 plus I is also the 0, though it's not given there, but we know that if a complex number is a 0, then the conjugate must be the 0. So the other 0 is 2 plus I. So x minus 2 plus I is also the 0. So let's go ahead and multiply this. So this gives us p of x equals a times x minus 1/3. Now we can multiply this. Okay, so let's write it this way first. X minus 2 plus I times x minus 2 minus I, and then we'll multiply. So p of x equals a times x minus 1/3. Now, when we multiply this, so let's go ahead and multiply. So x times x is x squared minus 2x minus xi minus 2x plus 4 plus 2i plus xi minus 2i minus I squared. Now, there are some terms that we can cancel. So we can cancel out xi and xi, because negative xi plus xi, they add to 0. Then 2i and minus 2i, they add to 0. So those are the terms that go away. Then we have p of x equals a times x minus 1/3. Then we have x squared, negative 2x is minus 4x. Then we have 4. Now I squared, so I squared is negative 1, and then we have a negative sign here that gives us plus 1. So that means this becomes p of x equals a times x minus 1/3. Then we have x squared minus 4x plus 5. Now we can multiply those two factors. So p of x equals a times, so when we multiply this, we get x cubed minus 4x squared plus 5x. So when we multiply by x, then when we multiply by negative 1/3, we get minus 1/3 x squared plus 4/3 x minus 5/3. Now let's go ahead and combine the like terms. So a times, so we have just 1x cubed. Then we have negative 4x squared and negative 1/3 x squared, which gives us negative 13 over 3x squared. And then we have 5x and 4/3 x, so that gives us 19, so plus 19 over 3x. And then the constant term is minus 5 over 3. Now we are not given any other condition. The only condition that we are given here is the um, the coefficients are all integer coefficients. That means there is no factor. So if we take a equals 3, so if we take a equals 3, then we get all the coefficient as integer coefficient. So that's what we are going to plug it in here. Okay, so we can take any value of a, but we are going to take a equals 3 because that's going to get rid of all the fractions. So p of x equals, if I take a equals 3, then I get 3x cubed minus, so when I multiply by 3, I get 13x squared. When I multiply by 3, I get 19x. And then when I multiply by 3, I get minus 5. So this is the required polynomial. That's all for this video. I'll see you again in the next video.